Right, maybe we should get started. So welcome everyone to TCS Plus. Before turning to the talk, I just wanted to say that TCS Plus is an online seminar that's been running for over 10 years. We're always looking for suggestions for papers, so please feel free to reach out to us through the Google form on the website. And I'd also like to thank the other organizers of TCS Plus, Kamal Kanong, Rachel Cummings, Emily Fox, Sumeka Garg, Yasmin Nazari, and Eric Weingarten. So with that out of the way, let's turn to today's talk, which is also the last talk of the year, last TCS class talk of the year. We're super excited to have Martin Costa, who's a PhD student at the University of Warwick, who will tell us about some exciting recent work on Vizing's theorem.
Okay, so yeah, thanks a lot to the organizers for the invite. And yeah, I'm very excited today to talk about our recent paper on edge coloring and where we show how to implement Vizing's theorem in near linear time. So if at any point anyone has any questions, feel free to ask either by unmuting yourself or typing something in the chat. I'd be very happy to keep this interactive if you guys want to. Okay, so to start off right from the beginning, what is the edge coloring problem? So as input to the edge coloring problem, we're given some graph, undirected simple graph G equals VE. And we want to compute a coloring on these edges, which is just basically labeling of the edges so that no two edges that share some common endpoint receive the same label, right? So no two edges that have some vertex in common are going to receive the same color. Okay, so the objective here is just to compute an edge coloring of the graph. And clearly, the number of colors that we need in order to compute such a coloring is going to be at least the maximum degree of the graph. And this is because if you take some vertex of maximum degree, all of the edges incident on it need to receive some different color. So really the interesting question here is how small can we make k, the number of colors, right? Because trivially, we could just assign every edge a different color and we'd already be done. So it was proved in 1964 by Vizing that it's always possible to compute a delta plus one coloring of a graph. Okay. And this is quite non-trivial and kind of surprising to me, I think. And in some cases, you do actually need delta plus one colors. For example, if you consider a triangle, here the maximum degree is going to be two, but you need at least three colors in order to be able to edge color this. And in general, it's actually NP hard to determine whether or not a graph is delta colorable. So from an algorithmic perspective, delta plus one coloring is really the best that we can hope to attain in polynomial time. So a natural question that arises when you're thinking about this from an algorithmic perspective is how quickly can we actually compute such a coloring of a graph? Okay. So Vizing's original algorithm is well, his original proof is algorithmic and immediately gives rise to an mn time algorithm for computing a delta plus one edge coloring of a graph. And this was subsequently improved upon by Gabow et al. And Arjomandi independently, and they showed how to obtain an m root n running time for this problem. And then for a very long time, there was no polynomial improvement here. And then much more recently, Cinnamon showed how to shave off. There's like a root log n factor in the running time of this bound from Gabow et al. And got the running time down to m root n without any log factors. And then very recently, so in between these results, there was actually a result that showed how to do a m log delta coloring for bipartite graphs, right? So in bipartite graphs, you can actually obtain an exact delta coloring. And it's been known how to do this in near linear time for over 20 years now. Okay, but for general graphs, there hasn't been a polynomial improvement in quite a while. And then very recently, there was a bunch of works that showed how to improve upon this runtime bound of Gabow et al.'s via polynomial factor using various different techniques that gave some polynomial improvements, and some results are better than others depending on the sparsity regime of the graph. And as our result, we kind of continue on this line of work and taking a very different approach to all of these recent results. We actually show how to compute a delta plus one coloring of a graph in near linear time, in m log delta time with high probability. And our algorithm also extends to multigraphs as well. So it was shown by Vizing a generalized version of his theorem is that if you have some graph of max degree delta and maximum edge multiplicity mu, you can compute a delta plus mu coloring. And an even older theorem by Shannon shows that any non-simple graph with max degree delta can be colored with basically 3 delta by 2 colors. And our algorithm extends to these cases as well and shows how to give a near linear time, m log delta running time for these problems too. Okay, so yeah, the focus of this talk is basically going to be to give describe this algorithm that obtains this near linear running time for general graphs, and this actually matches the best known running time for delta coloring in bipartite graphs, which has been known for quite a while now. Okay, so to start off, we're just going to go over some basic preliminaries and ideas that are very common in edge coloring that we'll be using in order to describe the algorithm throughout the talk. So the first basic idea that is used here in edge coloring is this idea of alternating paths, right? These are kind of like the basic combinatorial structure that our algorithm is built upon, right? So suppose you have some partial coloring of a graph, some partial delta plus one coloring, and you have some uncolored edge UV, right? And so here we can see this edge UV, and incident upon it, you have some blue red and some blue edge and some red edge incident on U, and some yellow edge and some green edge incident on V. And the key observation is that because we have delta plus one colors, we will always have colors missing at nodes, some color which is available, right? So here, for example, we can see that this node U is missing the color green, and this node V is missing the color red. And what we can do is we can consider the red-green alternating path that comes out of this node V, right? So V doesn't have any red edge incident on it, but it has a green edge incident on it. And then we can consider the red edge that touches this green edge and so on. And we can continue this process until we eventually kind of like construct a maximal alternating path and we can't continue this path. And one of the key observations within edge coloring is that by flipping this alternating path, we can make the color green available at this vertex V. And then this color green will be available at both endpoints of this edge, and we can just color this green and extend the coloring. And this is basically like the classic basic procedure for extending the coloring to some uncolored edge. The issue is that unfortunately, it might be the case that this edge kind of goes back to the other endpoint. And in this case, when we flip this alternating path, we do make green available at V, but we also make it unavailable at U. We basically flip what the available colors are, and we can't then extend the coloring to this edge. But we can observe that in order for this to happen, we basically need to form an odd cycle. So this can only happen in non-bipartite graphs. Okay. So if we just focus on this can only happen, yes, in non-bipartite graphs. So if we just focus on the bipartite case for now, this gives us a very natural algorithm for coloring such a graph, right? We basically scan through all of the uncolored edges in a completely arbitrary order. And while looking at some edge UV, we basically just assign it some arbitrary missing color at U. So here this is red, so arbitrary missing color at V, which is blue. And then we consider this blue-red alternating path that comes out of this edge. We flip this path, making blue available at both endpoints. And then we just color this edge blue. We can just do this for all of the uncolored edges in a completely arbitrary order, and this computes a delta coloring of the graph. And the time complexity that it takes to perform this step is just using very basic data structures proportional to the time that it takes to compute this path, right? So it's just proportional to the length of the path. And because the path has size, in the worst case, big O of n, because it's just a path, the complexity of this algorithm is just going to be mn, right? And this is basically how the proof of Vizing theorems work. Vizing's theorem works for general graphs with the additional kind of like construction of a small gadget to deal with this case where you have these loops, basically. Okay, and one useful insight that we will be using throughout this talk in order to kind of like try and speed up our algorithm is basically the observation that if we have lots of uncolored edges, which are, in different parts of the graph, and they're all missing the same missing colors at the endpoints, and we consider all of these blue-red alternating paths coming out of all of these edges simultaneously, we can show that the combined length of all of them is going to be big O of n, right? And this is just because if you look at the subgraph induced by red and blue edges, this is just going to be a bunch of vertex disjoint paths and cycles. So if instead of doing this one edge at a time, we can look at lots of uncolored edges together that have the same missing colors, and we try and extend the coloring to all of these together, we can basically get much more out of this big O of n time that we have to potentially spend flipping these alternating paths. We can make a lot more progress. And this is kind of like one of the key observations that we're going to be using in this algorithm, but I'll explain this in a little bit more detail later. This is just a high level idea. So we basically want to try and find a situation where we have lots of uncolored edges that are missing the exact same colors. Okay, so the second idea that's very standard in edge coloring that we will be using is this idea of Euler partitions, right? So given some graph G of max degree delta, basically you can split this graph up, efficiently split this graph up into two edge disjoint subgraphs that have almost the max degree, which is almost half of delta, right? And the exact way that you compute this is basically by computing like an Euler Tor of a graph, which is why it's referred to as an Euler partition. Basically, just add some matching so that there are exactly two edges that have odd degree, and then traverse like some Euler Tor of the graph. And as you do this, you kind of like alternately assign one edge to one subgraph and one edge to the other. And the details of how this construction work aren't exactly very important, but the point is that you can partition the graph into two edge joint subgraphs where the max degree in both of them is the ceiling of delta over 2. So almost exactly partitioning the max degree, but not quite. Okay, so for the rest of the talk, the main focus will be to basically explain the behavior of our algorithm on bipartite graphs, right? So it's already been known how to edge color bipartite graphs with only delta colors in near linear time for a long time, but that algorithm really crucially exploits bipartiteness in a way that does not generalize at all to general graphs. Here, the assumption of bipartiteness will be used purely to simplify some annoying technical details, but the will still kind of capture all of the main ideas that are required in order to make this algorithm work for general graphs as well. But because we will only be considering bipartite graphs, we will only need delta colors, so the algorithm will be presented for delta coloring bipartite graphs. And then at the end, if I have some time, I'll explain how this can be modified to work for general graphs too. Okay, so first things first, we're going to show how we can use this Euler partition approach in order to kind of like tackle this problem of edge coloring. And essentially, this gives us a divide and conquer approach for this problem. So we take our graph G, we partition it into G1 and G2, and then we recursively compute delta colorings on both of these graphs, where delta is the max degree of these graphs individually, right? So we recurse on G1 and G2, and then we have a ceiling of delta over 2 edge coloring for this graph G1, and a ceiling of delta over 2 edge coloring for this graph G2. And then we basically just take their union. And this gives us an edge coloring of the graph G, right? But the problem is that this now has delta plus 1 colors where, we're trying to delta color bipartite graphs, so we have one extra color. So what we do is we uncolor this one extra color class, and this gives us a matching of uncolored edges that has maximum size big O of n. And then what we want to do is we want to extend this delta coloring to also color this matching as well in m time, near linear time. And basically, if we can do this one part here, everything just falls into place and we get our algorithm. And the reason for this is that we just basically apply this, this recursive algorithm, and this gives us the following recursion, which you can solve to basically give you a near linear running time algorithm. So essentially what this means is that we can focus only on coloring the very last few uncolored edges in the graph, right? We can assume that the uncolored edges, A, form a matching, so they're vertexes from each other, and there's only big O of n of them. And then if we can extend the coloring to just this matching of uncolored edges in near linear time, then we're done. We get an algorithm that runs in near linear time as well by just using the divide and conquer approach that follows from using Eulerian partitions. So for the rest of this talk, we will basically just assume that we have a matching of uncolored edges and focus on extending the coloring to this matching of uncolored edges in near linear time. And this approach here, it extends pretty much completely seamlessly to general graphs as well. So in general graphs, we also just care about extending the coloring to a few uncolored edges as well. Okay, so now I'm just going to describe kind of like the high level overview of our algorithm, like exactly what it is that our algorithm does. So the idea is, like I said before, we want to extend some partial coloring to n uncolored edges in near linear time that form a matching. And our algorithm is basically composed of two separate components. The first one we'll refer to as color type reduction, and the second one we'll refer to as a uniform type color extension. And the idea here is basically that we want to do something kind of similar in spirit to this very simple bipartite algorithm that I described before, but instead of only coloring one edge at a time, we want to color many edges at a time in order to speed this up. And also, just as a very minor simplifying assumption, we can assume that the graph is basically like somewhat regular, so that the number of edges in the graph is big theta and delta. This is only to simplify a couple of like calculations and equations on the screen and doesn't really have any effect on the algorithm. Okay, so in order to describe this color type reduction, suppose we have some edge UV. And we can assign this edge a type, right? And the type of an edge is basically just the pair of missing colors that we've assigned to its endpoints. So the type of this edge here will be red, blue. And we can note that an edge might be of many types simultaneously if it has lots of many different colors that are missing at its endpoints. But we only really care about just like fixing one type for it. So we can just assume that every edge has some unique type. Um, and the second observation is that any edge of type alpha beta will have some alpha beta path starting from each of its endpoints. And the total number of types that we can have is delta squared, because these are basically just all possible pairs of colors that we can have within our coloring. So what this first component does, what this color type reduction algorithm does is it takes some matching of lambda uncolored edges. And in n time, right? So in time, which is much less than the number of edges in the graph, this is kind of like a sublinear time component in our algorithm. It ensures that a 1 over delta proportion of all of these uncolored edges have the exact same type, right? So it does something without changing what the uncolored edges are. So it doesn't extend the coloring to any edges or anything, but it somehow, changes the colors of the rest of the graph in order to ensure that a 1 over delta proportion of these uncolored edges have the exact same type. So notice that, for example, if you wanted to try and find a lot of uncolored edges here that had the same type without changing the coloring, the best you could guarantee is basically a 1 over delta squared proportion of them, because there's delta squared many types, right? So one of them has to appear like a 1 over delta squared proportion of the time. But here we're going to do something different. We're going to modify the coloring somehow in order to amplify the number of edges that have this type red blue. So we fix some type alpha beta, we do something to the graph, we amplify the number of edges that have this type, without changing where these uncolored edges are located, so that they remain vertex disjoint even after we do this kind of like color type reduction. And then the second step of our algorithm, this uniform type color extension, it takes all of these edges that have the same type alpha beta, and then it extends the coloring to all of them in n time. And this second part is quite straightforward. This basically just flips the alpha beta alternating paths that are touching these edges all at the same time. Okay, so the kind of like non-trivial, interesting part of this algorithm is the first component, how we amplify the number of edges that have this fixed type alpha beta. Okay, and then we can put both of these components together. So we take our lambda uncolored edges, we kind of perform this color type reduction. We increase the number of edges that have this specific type alpha beta. And in particular, we make a 1 over delta proportion of them have this type. Then we extend the coloring to all of these edges. Both of these two components run in n time. And then we just repeat this process. And we can repeat this process delta times. And after doing this delta times polylog many times, we will have extended the coloring to the entire graph. And because every single one of these iterations of increasing the number of edges that have this type and extending the coloring to these edges can be done in n time, and we do this, and this colors in a 1 over delta proportion of the edges. After doing this delta times, we've colored the entire graph, and the total running time will be roughly n times delta, which is big O of m, because we've assumed the graph is near regular, right? And here, if you want to get rid of this assumption of near regularity, you can actually show that both of these components of the algorithm can be implemented in m over delta time instead of n time. And that's really the only difference here. Okay. So now to explain how these components actually work. Okay, so component one, this color type reduction. So like I said before, we fix some completely arbitrary colors alpha and beta, and we want to increase the number of colors that have this type that are missing red at one endpoint, and blue at the other endpoint. Okay, so this is the high level framework that we employ in order to achieve this. So we say that an edge is social if it has type alpha beta, right? So if it's missing alpha at one endpoint and beta at the other endpoint. And let's suppose that less than, lambda over 100 times delta over edges are social at this point, right? If we already have that more than this many edges are social, then we're basically done. We have enough social edges that we've kind of already performed this color type reduction, and we can move on to this second component. So let's assume that we don't currently have enough social edges and we want to make more of them social. So the idea here is that we want to somehow change the coloring in order to make one more edge social without damaging any of the other social edges that we've already created. Okay? And we refer to this process as just like one iteration. So what our algorithm does is it repeatedly just creates one more social edge until we've made enough of them. And the idea is that we can implement a single iteration of socializing one more uncolored edge that isn't social yet in n delta over lambda time. And then because every single iteration will take n delta by lambda time, and we just want to repeat this until lambda by delta of these edges have become social, the total time we will spend performing all of these iterations will be big O of n, which is exactly what we wanted in order to be able to kind of get these components to have the desired running time. Okay. So I'll now explain how we can implement a single iteration of socializing one more of these uncolored edges in n delta over lambda time. Okay. So suppose we identify some uncolored edge xy that isn't social yet, and we want to make this edge social, right? How can we modify the coloring so that, red is missing at this endpoint x and blue is missing at this endpoint y? So let's suppose that we're in the bad case where we don't already have this guarantee, right? So we do have some red edge incident on x and some blue edge incident on y. Well, we know that X and Y will both be missing some colors, right? They just won't be the colors that we want, red and blue, but they will be missing some colors. So let's say that this node X is missing green and this node Y is missing purple. And if these two colors, like red and purple, happen to coincide, then we can immediately color the edge for free and we make progress, right? So let's suppose that these colors are different to each other and they're not red and blue. Then we can consider the the red-green alternating path coming out of X and the blue-purple alternating path that's coming out of Y. And notice that these alternating paths, these maximal alternating paths, are going to be completely edge disjoint because they have completely different colors, right? So what we can do is we can flip this path PX and we can flip this path PY. And flipping this path px will make green no longer available at x, but it will make red available. And flipping this path py will make purple no longer available to y, but we don't really care about this color purple, but it will make this color blue available, right? So this is the procedure. We take some random edge. We see, okay, it's not social. It doesn't have red available at this endpoint, doesn't have blue available at this endpoint. We find some colors that are available. This defines two disjoint alternating paths. And we just flip them both simultaneously. And this edge, after performing this operation, will not be social. So what's the problem here? Unfortunately, it's not quite this simple. The issue is that we can't guarantee that this path, px, for example, doesn't end at some edge that we previously processed and already made social, right? This might be the case. And if this is the case, then flipping this path will basically damage one of the edges that we had previously made social. So we can still we can still make this brand new edge XY social, but in the process, we'll be damaging some previously socialized edge. And we're not making any progress if this is the case, right? We're doing work, but the number of social edges isn't going to actually be increasing. And if this is the case, right? So if this edge, trying to make this edge social basically damages a previously socialized edge, we say that this edge XY is bad. But the thing to observe is that we can basically blame this edge UV, which is being damaged while trying to socialize this edge XY, as being responsible for this problem, right? And the key observation here is that every single already social edge can only be responsible for two delta many edges being bad. And the reason for this is, okay, why is this edge XY bad? Well, because the red-green alternating path that starts here ends at some previously social edge. But how many red slash other color alternating paths can start at U and end at other uncolored edges? Well, it's going to be at most delta. And this is because there are only delta red other color alternating paths coming out of U. And the locations of these and all of these edges here are vertex disjoint, right? So one of these alternating paths can only end at one uncolored edge. And then the same happens on the other side as well for the blue other color alternating paths. So every single one of these already social edges is responsible for creating two delta bad edges. But then this also implies that there can't be that many bad edges, right? Because we assume that we haven't already created more than lambda over 100 delta social edges, which means that the total number of bad edges is going to be basically lambda by 50. And in particular, this implies that at least half of the edges are good, right? So they're not social and they're also not bad in the sense that if we pick one of these and try and make it social by flipping these alternating paths, we're not going to damage any of the previously socialized edges that are already missing blue and red. Okay, so we can't, efficiently know which of these edges are going to be good and bad. Every single time we flip some alternating path, the structure of which edges are good and bad might change completely, right? So we can't keep track of these things when where they are, but we know that if we just sample one uniformly at random, the probability that it will be good is high. It's going to be at least a half. So what our algorithm does is it samples some uncolored edge XY uniformly at random that isn't already social. And we can just assume that this uncolored edge is going to be good. It happens with constant probability. And we flip these paths, Px and Py. And if we notice that after traversing these paths, it happens to end at some other previously socialized edge, then we're like, okay, this iteration failed. We just don't do anything. And we just sample another one again. And then the number of iterations that this process will run for an expectation is only going to be lambda over delta. And the key observation here is that, okay, what is the time that it takes for this process to like be carried out? Well, if you sample one of these edges uniformly at random, the time that it takes to make this edge social is just going to be proportional to the sum of the lengths of these paths that you have to flip. And because every single one of these edges it has associated to it some unique alternating path that gets flipped if we try and make this edge social, the total length of all of these paths is only going to be n times delta. And this is because the length of all red and other color alternating paths is n times delta. And the length of all blue slash other color alternating paths within the entire graph is also n times delta, right? So by some very basic averaging argument, you have unique alternating paths from this set being assigned to, roughly lambda uncolored edges. So the average length of one of them is going to be only n delta by lambda. And this gives us the running time bound that we wanted for a single iteration of this process, right? So then we have this running time bound of n delta by lambda for one iteration. We perform lambda by delta many iterations, and this gives us a running time of big O of n to create a 1 over delta proportion of these edges to have the exact same type. And yeah, once again, so this bound really just follows from a very basic averaging argument, saying that all of the paths that have like alpha as one of the colors, the total length of all of these is just going to be n times delta, and the same holds for beta. Okay. Okay, so now onto the second component, which is quite a bit simple. So once we've done this pre-processing, we've made a 1 over delta proportion of these edges be missing these colors alpha and beta, we now want to extend the coloring to all of these edges. And here, this is very similar to sort of this argument for the simple algorithm for bipartite graphs that we saw before. You just consider all of these red-blue alternating paths starting at these nodes, U1, UI, all the way up to U lambda for all these uncolored edges. And notice that these paths, they're not necessarily distinct from each other. Some of them might actually be the same path, starting and ending at different one of these nodes. But we can assume, just for simplicity here, that all of these UI are on one side of the bipartition of the bipartite graph, and the VI are on the other side of this bipartition of this bipartite graph. And this basically says that none of these paths PI that start at UI can end at some VJ. Otherwise, this would just be creating an odd cycle. And this means that we can flip all of these paths kind of in parallel, basically, and their total length is just going to be big O of n because the subgraph of all of these alpha beta edges is just a bunch of edge disjoint paths and cycles, vertex disjoint paths and cycles. And after flipping all these paths, blue is available at all of these nodes, and then we can just color in these edges with blue, and we're done. We've extended the coloring to all of these edges in only n time. This can be done very easily. Okay. So then putting these two things together, you take your uncolored edges, you make a 1 over delta proportion of them have the same type, and then you extend the coloring to these edges. This part can be done in n time repeatedly, and after doing this delta times polylog times, you're done. You've extended the coloring to the entire graph, and you have a near linear time algorithm for computing an edge coloring based on alternating paths. Okay. Now, one thing to observe is that this first part of the algorithm, where we're taking our edges and we're making them social, here we're not using this assumption of bipartiteness at all. This works completely as is for general graphs. The location where we're using bipartiteness is basically here to ensure that when we flip these alternating paths, you can't have basically a cycle going from U1 to V1. Because if you had this, then even if you flip this path, you can't then extend the coloring to this edge. So this is the one and only part in the entire algorithm that I've described so far, which is actually using bipartiteness. All right. The other part, the part where we're making these edges social, this doesn't use bipartiteness at all. And this part here was somehow, the conceptually complicated part. So then the question is, okay, well, why can't we combine this with the Vizing fan machinery that allows us to compute edge colorings in general graphs in order to make this algorithm work for general graphs? So what goes wrong if we try to do this? Okay. So recall the challenge is, these odd cycles forming in general graphs, right? So in order to basically deal with these, Vizing introduced what is now referred to as a Vizing fan. So I'm going to briefly go over the construction here, but it's a little bit technical, but the details aren't too important. So suppose we have some uncolored edge with we'll refer to this as the center of the fan U, and this is missing red. So in a general graph, instead of just considering the blue-red path coming out of U, we do something slightly different. We consider the first blue edge, and we consider the other endpoint of this blue edge that's incident on U. Notice that if there is no such edge, then blue is also missing at U, and we can immediately color this edge blue, and we're done, right? And because we have delta plus 1 colors, this other endpoint, will be missing some other color. So let's say this is green. And then we consider the green edge incident on U, and then the other endpoint of this edge will be missing some other color. Let's say that this is yellow. And we just continue this process, adding more and more edges to this fan, so as we call it. Eventually, one of two things will happen. The first one is that one of these edges will be missing some color, which is also missing at U, in which case we can basically move all of these colors down one edge. We can rotate this fan, and then we're left with some uncolored edge, which is missing red at both endpoints, and we can color this in red, and we're done. The second case is where we encounter some edge where the other missing color at the endpoint is a color that we've already seen before. So here yellow is this color. We've seen yellow twice within this fan. And then we can't just add the same edge into the fan again because this doesn't really achieve anything. So instead, what we do is we basically consider the red-yellow alternating path that's coming out of this vertex U. And now, depending on exactly some different cases here, um, we might do something different. But the point is that we can extend the coloring to this uncolored edge by flipping this blue-red alternating path and then just rotating some colors around U. Exactly how we rotate these colors around U doesn't really matter very much, right? So in the first case, if this path doesn't end at this node W, then we can flip this path and then rotate these first colors in the fan. And in the second case where it does end at W, we can flip this path and rotate colors around all of these edges, okay? This part here doesn't really matter too much, but the point is that this whole thing can still be implemented in time proportional to the length of this path, plus delta time for rotating colors around this fan. And this thing is also going to take big O of n time, and then this gives us the mn time running time for Vizing's theorem. Okay. But what I want to emphasize here is that the main problem with this Vizing fan construction is that we don't have control over what the second color in this alternating path is, right? One of the key things in our previous algorithm was that the time that it took to extend the coloring to all of these alpha beta socialized edges was only big O of n. And that's because the total length of all these alternating paths was big O of n because they all had the exact same colors, blue and red, right? But here, even if we have all of these social edges where blue is missing at one endpoint, red is missing at the other endpoint, and we consider the alternating paths generated by the Vizing fans at these edges instead, the secondary colors in these paths might all be different, right? They're not necessarily going to be blue. And this is basically the problem. So you can control the first color, it will always be red, but you don't have control over the second color. It's a function of the properties of the missing colors, incident on the neighbor's view, and this is very hard to bring under control. And because we don't have control over the second color, the averaging argument becomes much weaker because now the total length of these paths isn't big O of n, it's big O of n times delta. And this leads to a delta factor larger in the running time. So the key insight is that instead of using Vizing fans, we actually use a different type of fan that works in general graphs, but does actually allow us to control both of these colors. And this is what we refer to as a U fan. Okay, so a U fan is a pair of uncolored edges, U and V, which share some common node U and have these what we refer to as leaves, V and W, where the missing color here at this node U is just some color red. And then these two here have to be the same missing color. So it's just a pair of uncolored edges that form a V where the leaves of this fan are missing the exact same color. And the reason that this is useful is because now if we just consider this red-blue path that's coming out of U, and it does happen to end at V, if we flip this path, it will be the case that we cannot extend the color to this uncolored edge UV. Just like before, this is now going to be a problem. But now, after doing this, blue becomes available at U, and it's still available at W. Because this alternating path, it can end at one of these two endpoints, but it can't end at both. And the observation is that regardless of whether or not this path ends at one of these two endpoints, after flipping it, we will always be able to color in one of these two edges. And then we can extend the coloring to this edge, and this is what we refer to as activating a U-fan. Now, this is kind of different because we need two uncolored edges touching at the same location, and they need to satisfy this constraint that they're both missing the same color at the endpoints. So it's actually pretty hard to even create this object in the first place, right? We're given uncolored edges completely for free in this recursion. We actually have to build U-fans, and it's pretty non-trivial to actually build U-fans. But the key observation is that once we have these U-fans, we can control the colors that are going to be incident on the alternating paths that we construct. And we can control these colors just by doing some completely analogous stuff by flipping the alternating paths starting at these endpoints just like before. So these U-fans, they basically play an analogous role to uncolored edges in bipartite graphs, but they play these role for general graphs as well. So we have all of these UFans, and we can socialize them in the same way as before, and we can flip these alternating paths and then extend the coloring to them just as before. One of the differences is also that when we activate a UFan like this, we color one of the two edges in that it contains, not both of them. But still, if we have like a large number of UFans and we activate all of them, we color half of the edges. So we're kind of still making progress, right? Okay, so at a high level, how does the kind of like algorithm work for general graphs now? So the setup is exactly the same as before. We do this Eulerian partition stuff, and we just want to extend the coloring to basically the big O of n remaining uncolored edges in nearly linear time, just as before. Okay, and now suppose that we have lambda uncolored edges, then the algorithm has basically two phases. So in the first phase, we want to either A, extend the coloring to a constant fraction of these uncolored edges using Vizing fans somehow in near linear time. Or if this isn't possible, we want to basically create lambda U fans out of these uncolored edges. We want to move these uncolored edges around the graph and we want to put them into U fans. And then in the second phase, given that we've created a bunch of U fans, we then want to basically extend the coloring to a constant fraction of the edges contained within the U fans. All right. So this second phase of the algorithm, so comparing it to the two components that we had before for bipartite graphs, the first component for bipartite graphs would basically make a 1 over delta proportion of the uncolored edges have the same type, and then extend the coloring to these edges. Now for UFans, it's a little bit different. Instead of having these uncolored edges, we have UFans, right? So we are modifying the types of UFans by flipping alternating paths, not modifying the types of uncolored edges. And also, instead of extending the coloring to all of the, uncolored edges, we can only extend the coloring to a constant fraction of the edges that are contained in the UFans. But I claim that basically the algorithm that achieves this is completely analogous, just modifying a few technicalities in order to accommodate the slightly different definition of UFans. But the kind of like overall picture is basically exactly the same. So I won't elaborate on this part anymore. The technical details and the conceptual parts are really the same. So the only part that remains is like, okay, how do we actually create UFans? These are quite non-trivial objects, and it's not immediately clear that this is even possible. Okay. So the idea here is now in big O of m time, we want to take a lambda uncolored edges and either color lambda color lambda of these edges in near linear time or return lambda U fans. We want to do one of these two things. So what we can do is we can, take our uncolored edges and let's fix some arbitrary color red. And then this thing will run in basically delta iterations for all of the kind of like different colors that are missing at these endpoints. And what we do is we construct the Vizing fans at these uncolored edges, all of which have the same missing color red at the center of the Vizing fan. Now, if two of these Vizing fans happen to intersect by chance, we can basically rotate some of the colors in the Vizing fans to ensure that two of these two edges within the Vizing fans that happen to intersect are left uncolored. But because they're both of these Vizing fans are missing red at their centers, this thing now forms a UFan. It'll be this UFan here specifically will be a red purple type UFan. And we can basically kind of like take this UFan out and we can kind of put it in our collection of UFans that we've created so far. Okay. So if these Vizing fans intersect, then we're in good shape because we can immediately create a bunch of UFans. Now, in the second case, we can assume that these Vizing fans are all vertex disjoint from each other. They don't overlap at all. And we can then start to construct the Vizing chains that come out of these Vizing fans in parallel. Now, if any of these paths happens to finish, then we can flip this path and extend the coloring to this edge, and we've made some progress. Otherwise, these paths will intersect at some point, right? And the idea here is that the total length of all of these paths is actually not going to be that long because all of the paths have are either vertex disjoint or we find some intersection. And whenever we find some intersection, we basically do the following. We can shift the uncolored edges down these alternating paths in order to create a U-fan, right? So they intersect here and we can shift rotate these U fans so that these edges are left uncolored, and we can shift the uncolored edges down. And once the uncolored edges are located here, we can notice that both of these two nodes will now be missing red, and this thing here now forms a U fan. And the key here is basically to notice that because these paths, as we're constructing these paths, they're always vertex disjoint at all times. Their total length is basically going to be proportional to the number of red edges that there are in total across the entire graph, which isn't going to be that much, right? And then if we do this for all of the different colors, the total running time of all of these constructions is only going to take big O of m time across all of them, okay? So this edge disjointness of these paths, well, vertex disjointness of these paths is kind of what allows us to implement this thing efficiently. And this is basically how we construct the UFANs. And then after we constructed all of these UFANs, either we notice that we constructed a lot of UFANs and we proceed to the second phase, or we notice that actually we colored in a lot of these uncolored edges, and then we just go back to phase one again. And then this is basically how we extend the algorithm to work for general graphs. Okay, so to conclude, in this talk, we show how to delta plus one edge color graph in near linear time with high probability. So here we didn't really talk about the polylog dependence. The algorithm that we described here has some slightly larger log dependence, but in various places you can optimize certain things in order to bring this down to m log delta, also using some other results as black boxes. And this basically gives us a running time which matches what is currently known for bipartite graphs as well. And yeah, I think two interesting open questions here are whether or not this algorithm can be made deterministic. So the one place in this entire algorithm where we use randomness is when we basically sample which edge to make social. So even though we know that at least half of them are going to be good in the sense that if we sample this edge to make it social, flipping this alternating path will succeed. We have no idea which edges are the ones that are good and which are the ones that are bad. And even flipping one alternating path can completely change which ones are good and which ones are bad. So it's really quite unclear how this step can be de-randomized. And the second question is how can we potentially remove this extra log factor? Even in bipartite graphs, can we remove this log factor and bring this down to exact big O of m running time? Okay, so that's everything I would talk about. So thanks a lot, and yeah, I'd be happy to answer any questions if anybody has them.
Thanks, Martin. Um, do people have any questions right now? I guess maybe a stupid question, but you said that there's hardness, like computing the like determining the uh, edge chromatic number is NP hard, right? Is there like is it like determining if it's K versus 2K is NP hard or
I don't remember exactly, but I think even for it's like even distinguishing very low values is NP hard. So I don't know exactly, but I think it's like even determining whether or not a graph is like three or for even for very low degree graphs, like graphs of degree three or
okay,
something,
okay, okay,
it's
okay.
NP hard to determine this. So
Is
yeah,
it
I think it is very hard. Yeah, in order
okay?
to detect this. Yeah.
Yeah, I guess I was asking because it's this might not make sense, but I don't know if you could get like a is it possible to ever hope for like a delta edge coloring as opposed to a delta plus one?
I mean, so there are specific cases where it's possible to delta edge color graphs. So, for example, low arboricity graphs, it's possible to compute delta edge coloring stuff. So, if you can guarantee that the arboricity of a graph is sufficiently smaller than the maximum degree by some constant factor, then you can guarantee that a delta edge coloring exists.
Hmm.
Um, But yeah, I mean, I think the unfortunately this hardness result says that like okay, you'll be able to find some specific classes like
Yeah,
sufficiently low
yeah,
verbosity graphs, bipartite graphs, where you can compute a delta edge coloring, and sometimes you can also do this fast as well.
yeah.
But in general, for yeah, I mean arbitrary graphs, I don't think
Yeah,
this is possible.
that makes
And I
sense.
think yeah, there's also like this like I think it's like a Brooks theorem result for vertex coloring, right? Distinguishing between delta plus one and delta colorable
I see.
vertex colorable graphs, but yeah, I don't think in general, I don't think it'll be possible to obtain something like this for edge coloring. This
Okay.
shouldn't be possible, yeah.
And which of these previous results are randomized? Is Vizing's original algorithm also randomized, or is it deterministic?
Yeah, so Vizing's original algorithm doesn't require any randomness because it's just basically computing a Vizing chain at every single
Okay.
edge. Um, yeah, so out of these results, this one, I think this is deterministic, or some variant of it can be made deterministic. Same with Cinnamon's algorithm. And then out of these recent results, yeah, I think all of these are quite randomized. Yeah.
Yeah. Yeah.
Unfortunately, I think even de-randomizing any of these would be quite challenging.
Hmm. So,
I think somehow like a lot of them rely on individual components that can be implemented in sublinear time, and de-randomizing these would be quite hard, I think.
yeah.
Yeah.
I'm going to stop the recording and we can take more questions offline. Thanks again, Martin. Yeah.
Yeah, thank you very much.